welcome to this lecture number 10 of our course on fundamentals of transport processes, where we had just completed the derivation of the mass conservation equation and we were about to start the derivation of the momentum conservation equation. Okay. So, we had used vector identities and tensor identities in order to derive that mass conservation equation in a simple manner, without reference to the underlying coordinate system that is used to analyze the problem. Okay. So, in that sense, the derivation that we did treated vectors and tensors as objects in themselves without reference to a coordinate system. Let us just briefly review that first before we go to the momentum conservation equation. So, now, so, the idea of the derivation of the mass conservation equation was as follows. If I have some volume V, okay, let me expand that out, some volume V. Okay. This is within the fluid. So, there is a velocity field that is defined at each point within the volume and outside, of course. There is a velocity field defined at each point within the volume. There is a velocity field defined at each point on the surface. So, there is a fluid velocity field that is defined at each point. It may vary with position, okay, but there is a well defined fluid velocity field. Okay. Now, if I consider the surface of this volume to be moving at the same velocity as the fluid at that surface, the fluid velocity at that surface is equal to the velocity with which the surface moves. So, in that sense, this volume is now a function of time. It moves with time along with the fluid, okay. A Lagrangian reference frame, if you will, okay, moving with the mean velocity of the fluid. So, at some later time, this volume will be at some other location. Okay, depending upon the fluid velocity on the surface, this volume will be at some other location. So, at the initial time, say t, the volume was at this location. At some later time, t plus delta t, it has shifted. And whatever fluid material points, fluid molecules say, okay, whatever fluid material points that were moving at that same velocity as the mean fluid velocity, those that were inside the volume will continue to be inside the volume, those that were on the surface will continue to be on the surface, and those that were outside will continue to be outside. That is because if we consider if a material element were to move from inside to outside this volume, if a material element were to move from inside to outside this volume, it would have to cross one of the material elements on that surface in order to move outside. Right? Obviously, if it goes from inside to outside, it has to cross the surface. And if it crosses the surface, it implies that the velocity has two values at that particular position at that time, because the one from inside is moving outside. So, it is moving faster than the surface material element. Therefore, it has to cross the surface. That means that the velocity has to be two valued at that location. However, the velocity vector, as we said, is a function of position and time. It has only a single value at each position and at each time. Therefore, material elements cannot cross from inside to outside. So, what remains inside continues to remain inside, what remains outside continues to remain outside, and what is on the surface continues to remain on the surface. Okay. So, therefore, if I were to write a mass conservation equation, since what was inside continues to remain inside, that means that the mass within this volume as it is moving is independent of time. The mass within this volume is d by dt of the integral of volume times the density, where this volume is now a function of time. The rate of change of mass within the volume is equal to 0, or the mass within the volume is a constant. Okay. So, that is the mass conservation condition. Now, this was written for a moving volume element, whereas we always define our velocity, density, etc., with respect to a fixed coordinate reference. Therefore, we have to translate what is in this moving element into something that is fixed in space. Okay. So, you have a moving element and there is some change, okay. The change in the mass within that element has to be equal to 0. As this moves, there are volumes, okay, in front, okay, which it occupies after this time, okay, which enter this differential volume. There are ones at the back which leave. Okay. So, the change in mass within this volume is going to be both due to what has entered as well as what has left, as well as due to the change in density within this volume itself. Okay. The density within this volume is changing, okay, in time. It is a function of position and time. So, because of that, there will be a change in mass. In addition, some mass that is ahead is coming in, some mass that is behind is left behind, because the volume has vacated that position. Okay. Therefore, that sum of what comes in, what has been left behind, plus the change in density within this volume itself due to the the change in mass within this volume itself due to the change in density, the sum of all of those three has to be equal to 0. Okay. The change in mass due to the change in density within the volume itself is of course just the integral of the volume of partial rho by partial t. Okay. That is the rate of change of mass within this volume due to the change in density itself. And the sum of the total mass that comes in and leaves because this volume is moving. Okay. If I define the outward unit normal to the surface at each location as n, okay. If I define the outward unit normal at each location as n, then the distance moved by a patch on the surface is going to be equal to the velocity dotted with n. U dot n is going to be the distance moved by a patch of the on the surface. Therefore, the volume that comes in is going to be equal to ds, the patch surface area, times u dot n. That increases the volume if u dot n is positive. So, that the velocity vector is in the same direction as the outward unit normal, then there is an increase within this volume. If it is negative, the patch is the surface has left behind the volume, okay, and therefore, the change in volume is negative. However, u dot n also is negative. So, that automatically takes care of just saying is it as u dot n automatically tells you whether it has come in or left. Okay. So, on that basis we had shown that this second part due to the volume that is coming in and the volume that is leaving is integral ds rho times u dot n. That has to be equal to 0. Okay. Mass conservation equation, use the divergence theorem, okay, to write this as integral dV of partial rho by partial t plus the divergence of rho u is equal to 0. Okay. Simple use of divergence theorem. Once that is done, we know that this, even though it is a volume integral over a small volume, this has to be satisfied for each and every volume. Okay. In fact, even if I shrink this volume to a point, limit as delta V goes to 0, okay, this condition is still satisfied. That means that it has to be satisfied at each point within the fluid. Okay. So, the mass conservation equation becomes partial rho by partial t plus del dot rho u is equal to 0. That is the fluid mass conservation equation. Briefly, we had also applied it to the concentration equation for mass transfer and the energy equation for heat transfer. Okay. In that case, the concentration, the mass of solute within a differential volume, okay, is going to be equal to integral dV of the concentration of the solute, okay, d by dt integral dV of the concentration. Concentration is mass of solute per unit volume. Okay. So, this is the total mass of solute within this volume. Of course, that is not 0, okay. That is not 0 because you could in general have a flux of the solute coming in or going out of this volume due to temperature due to concentration gradients. Okay. So, for example, if I had this volume here, okay, if I had this volume here, there could be a flux, okay, of the solute which tends to increase the concentration within this volume. There could be a flux of solute which tends to increase the concentration within this volume. It increases the concentration if the flux is inwards, that is it is opposite to the outward unit normal. In all of these I define the outward unit normal as n. Okay. So, there is an increase in the mass within this volume if the flux is inwards. Okay. So, the flux is defined as positive if it is inwards, that is it is opposite to the outward unit normal. Okay. So, the net increase in mass within this volume is going to be integral over the surface of minus q dot n. Okay. So, if q is along the direction of n, there is a decrease in mass within this volume. If q is opposite to the direction of the outward unit normal, there is an increase in mass within this volume. This was all that I had done in the previous lecture, but in general, if you had some sources of mass due to say some reaction or something within this volume, if I had a source of mass due to a reaction within this volume, I could incorporate it quite easily. Okay. This just becomes integral dV times the source, okay, which is a function of position. Okay. So, I could have some reactant concentration reacting to give you a product. S is the source of mass per unit volume per unit time. Okay. Integrated over time gives me the source of mass per I am sorry, integrated over volume gives me the source of mass, the amount of mass increase in this volume per unit time. Okay. So, this will be the equation if I had sources or sinks. Okay. If it is a source, it will be positive. If it is a sink, it will be negative. So, now this I can use my Leibniz rule once again. Okay. Integral dV partial c by partial t plus integral over the surface ds of c u dot n is equal to integral ds of minus q dot n plus integral dV of the source. Now, I have two surface integrals which are both some vector dotted with the unit normal integrated over the surface. I can convert both of them into volume integrals using the divergence theorem, and you will get integral dV partial c by partial t plus the divergence of c u is equal to integral dV of, okay, there is a negative sign here, minus divergence of q plus integral dV of S, the source term. Okay. Once again, this has to be true for each and every differential volume. So, my concentration equation becomes partial c by partial t plus del dot C u is equal to minus del dot q plus S, where S is the source term. Okay. And if I use my constitutive relation for, once again I wrote the heat flux instead of the mass flux. So, let me just replace this by J to avoid confusion, minus J. And once again, if you use the constitutive relation, J is equal to minus d grad C, okay, you get d del square C for the divergence minus the divergence of J. Okay. So, this is the simple extension. We had derived these equations in a rather laborious way in fundamentals of transport processes 1 by taking a fixed volume and then looking at what comes in and what goes out. Whereas, if you just look at moving differential volumes, that is the big advantage here. Okay. You treat vectors as objects in themselves, consider it on a moving reference frame, where the mass has to be conserved, and translate or shift or do a transformation of that moving reference frame onto a fixed reference frame, and you get the conservation equations quite easily. So, my conservation equation was partial rho by partial t plus del dot rho u is equal to 0. I can expand it out to write it as partial rho by partial t plus u dot grad rho plus rho del dot u is equal to 0. And the first two terms put together is just the substantial derivative in a reference frame moving with the mean velocity of the fluid. Okay. So, this is the definition d rho by dt. Okay, d rho by dt is a substantial derivative. Rho at x1 plus u1 delta t, x2 plus u2 delta t, x3 plus u3 delta t, t plus delta t, minus rho at x1, x2, x3 t divided by delta t. So, it's in a reference frame that is moving with the same mean velocity as the fluid. So, as the difference in the density at two locations which are separated by delta x is equal to u delta t. For future reference, it will also be convenient for me to write this in indicial notation, in which case my conservation equation will be partial rho by partial t plus d by dxi of rho ui is equal to 0. Okay. Repeated index, dot product, divergence reduces to a scalar. Okay. Also, in case the fluid is incompressible, what is meant by incompressible is that d rho by dt is equal to 0. The substantial derivative is 0 in a reference frame moving with the fluid velocity. If the fluid is incompressible, then for an incompressible fluid, you have the divergence of the velocity is equal to 0, or partial ui by partial xi is equal to 0. If you recall, we had defined the stream function in 2 dimensions for an incompressible fluid. Whenever divergence of a vector is equal to 0, it can always be written as the curl of some other vector, and we used that to define stream function in 2 dimensions. Okay. So, that is the mass conservation equation. Next, we will go on to the momentum conservation equation. Okay. The fundamental principle in the momentum conservation equation is Newton's law. Rate of change of momentum is equal to sum of applied forces. Only thing, this rate of change of momentum we are going to define on a moving volume element. Some volume element which at some later time goes to some other location. Okay. So, the basic principle, rate of change of momentum applied forces. Okay. Rate of change of momentum is equal to sum of applied forces. Rate of change of momentum in this moving differential volume, okay, is d by dt integral of Vt dV times the mass. Okay, it's the mass times the velocity. Mass is dV times rho, and the local velocity is u. Note, I am using indicial notation here. I have used ui because u itself is a vector. So, this momentum has 3 components, and I am writing the equation for each of these 3 components separately, okay, except that I am not expanding out the components. I am just writing ui as the representative of one of the components. One free index implied there is one summation, one unit vector. Okay. This is equal to the sum of the applied forces. Okay. The applied forces in general could be of two kinds. One is what is called a body force, that is a body force which acts on the entire volume of the fluid. Okay. Examples are gravitational force. So, if I have a volume, then the gravitational force is equal to the mass within that volume times g, okay. And or a centrifugal force which is also proportional to the volume itself. Okay. So, these are volumetric forces, they are proportional to the entire volume of fluid. Okay. So, this will be of the form integral dV times the mass times the acceleration. Okay. Let me just write this as an acceleration. Okay. Acceleration is also a vector. Okay. AI is the acceleration vector. For example, if the gravitational force was acting vertically downwards in this figure that I have, this AI will be equal to minus g times E3, okay, in this figure. Okay. But we do not have to consider a specific form of the acceleration itself, we will just consider it as a general acceleration due to a body force. Okay. So, that is the first part, and the second is you could also have forces that are applied on the surface of this volume. Okay. So, let me call this as a surface force. It is an integral over the surface ds times the force per unit area R I, okay, integral over the surface ds of the force per unit area R I. Okay. Surface force, of course, is the flux of momentum across the surface. Okay. The flux of momentum across the surface is resulting in a force which is applied on the surface, except that R I is defined as the force exerted on the surface, okay, whose outward unit normal is n. Okay. So, this surface force is similar to the surface flux that we had for mass conservation equation or the surface flux for the energy conservation equation. So, there is a surface flux in the momentum conservation equation, and you would expect that we will have to write a constitutive relation for this surface flux sooner or later. Okay. We will come back to that. The body force is of course specified for you. If you know what the gravitational acceleration is, you know what the body force is, or if you know what the centrifugal acceleration is, you know what the body force is. Whereas the surface force is due to the deformation of the fluid. Okay. Just as the mass flux was due to the gradient in concentration, the heat flux was due to gradient in temperature, you would expect this surface flux to be related in some way to the gradient in momentum or the gradient in velocity. Okay. We will come back to that. First, how do we apply the Leibniz rule for this left hand side? Okay. d by dt integral dV of rho ui, okay, integral over the volume. Okay. The Leibniz rule, one part due to the change in momentum within the volume itself, okay, that is going to be equal to dV partial by partial t of rho ui, okay, plus a second part due to the volume that comes in and goes out as this differential volume is moving, okay, because there is some fluid that is coming into this differential volume as it's, or some locations coming into this differential volume as it's moving, and some locations are being left behind. Okay. So, this is going to be equal to u dot n times the quantity itself. For the mass conservation equation, this was equal to rho times u dot n, because u dot n times ds was the volume that came in. Okay. Momentum similarly, rho ui at that location times u dot n. Okay. This is where it is useful to have indicial notation, because that u dot n I can write it in indicial notation as uj nj. Okay. Repeated index dot product, j is different from the index I, which is the direction of the momentum itself. Okay. It is different from the index I, which is the direction of the momentum itself. Okay. So, on the second term, surface integral of n dotted with something. Okay. that thing is now a second order tensor, because n is now dotted with rho ui uj. Okay. So, it is dotted with a second order tensor. Okay. So, integral of n dot something is equal to the integral over the volume of the divergence of that same thing. Okay. Does not matter whether it is a vector or a tensor. Okay. I can always take the divergence of a second, third order tensor, as I had shown you in the previous lectures. Okay. So, this just becomes equal to integral over the volume of dv partial by partial t of rho ui plus integral over the volume of partial by partial xj of rho ui uj. Note that the index that I use for the divergence has to be the same index as that for the unit normal. N dot something integral over the surface is equal to the divergence of that same thing integrated over the volume. So, I have to use the same index in both those places. So, this is the Leibniz rule as applied to this particular case, the momentum conservation equation. Okay. And so, this is the left hand side of the equation, the rate of change of momentum. On the right hand side, I have the sum of applied forces. One is volumetric force, the other is a surface force. And as I said, the surface force is due to momentum flux. Let us look at that a little more carefully. Okay. If I have a volume with some unit normal n, okay, the surface force R I is the force that is exerted on the surface, okay, of this volume. Okay. That is the force exerted by the outside fluid on the inside fluid. Okay. So, if I expand out this little differential volume here for you, okay, this is the surface. Okay. It has an outward unit normal, okay, and the fluid outside is exerting a force on the fluid inside. The fluid outside is exerting a force on the fluid inside, which is changing the momentum of the fluid inside, and that is what is coming into the momentum conservation equation. Okay. So, the fluid outside is exerting a force on the fluid inside. Okay. So, this is the force exerted by the outside fluid on the inside fluid. Okay. Let me just use a red for that. This is the force exerted by the fluid outside on the fluid inside. Okay. But we know from Newton's third law that the fluid inside exerts an equal and opposite force on the fluid outside. Okay. So, therefore, the fluid inside will exert an equal and opposite force on the fluid outside. Okay. So, this is the force that is exerted by the fluid inside on the fluid outside. Okay. For the fluid outside, the outward unit normal, okay, for the fluid outside, the outward unit normal is actually pointing into this volume. Okay. That is the outward unit normal for the fluid outside. Okay. So, the outward unit normal for the fluid outside is in this direction, it is pointing into the volume. Okay. Therefore, if I have a surface force, okay, for a given volume, for a given unit normal n, this is the unit normal for the outward unit normal for the fluid inside. Okay. If I have a surface force for that, if I consider the opposite, the force exerted by this fluid on the outside fluid, okay, I have interchanged the direction of the unit normal and the direction of the force also changes. Okay. If I reverse the direction of the unit normal, in which case I am looking for the force exerted by the fluid inside on the fluid outside, the direction of the force reverses. So, therefore, R I for a unit normal n is equal to minus R I for the unit normal minus n. Okay. This dependence on the unit normal suggests that I can write R I of n as T I j n j. Okay. You can see that with this specific form T I j n j, where T I j is now defined at a location, it does not depend upon the unit normal anymore. Okay. It is defined at each location in space independent of the unit normal. If I can write it this way, it satisfies this reversibility criterion. Okay, it satisfies this reversibility criterion. Okay. You can show that this criterion is actually valid for any differential volume using what is called the Cauchy construction. And the way it works is as follows. Okay. Let us take a small tetragonal volume element of fluid, okay, that looks something like this. So, let me just draw it larger so that it is easier to see. Let us take this small tetragonal volume element of fluid. Okay. So, it is bounded by 4 surfaces. It is bounded by 4 planar surfaces. One is the x1, x2 plane, x2, x3 plane, x1, x3 plane, and this slanted surface, the surface that is an angle to all of these 3 planes. Okay. So, this surface that is at an angle has an outward unit normal which is coming out of the plane. Okay. So, this has an outward unit normal that is coming out of the plane, okay, perpendicular to this surface. The other 3 surfaces have outward unit normals in the minus E1, minus E2, I am sorry, this is minus E3. This is in the minus E2 direction. And minus E1 direction here. Okay. The minus E1 normal is pointing behind, minus E2 in the left, and minus E3 downwards. So, these are the 4 outward unit normals for this surface. Okay. So, what is the net force due to these surface forces on all of these 4 surfaces? Okay. The net force, okay, so let me first write down the total areas that are perpendicular to each of these. Okay. So, I will call as the area in the x1, x2 plane, I will call it as ds3 because it is perpendicular to the s3 direction. Similarly, this area in the x1, x3 plane, I will call it as ds2. The area in the x2, x3 plane, I will call it as ds1, okay, that is behind there, ds1. And this area that is at an angle to all 3 planes, I will call it as ds. Okay. As I said, R was the force exerted per unit area. Okay. So, the total force exerted, okay, due to the surface forces will be equal to ds times the force per unit area at a surface whose unit normal is in the plus n direction. Okay. So, this is n, the normal that is coming out of this angled surface. Okay. So, this is ds times r I of n, okay, plus the contribution along these 3 planes. Okay. r I of minus E1 plus ds3 times r I of minus E3. Okay, that is the total surface force. Okay. And I also have this condition that when I reverse the unit normal, okay, when I reverse the unit normal, the direction of the force changes. Therefore, r I of minus E1 is equal to minus r I of E1, r I of minus E2 is equal to minus r I of E2, and so on. Okay. So, therefore, I can write the total surface force as ds r I of n minus ds1 r I of E1 minus ds2 Ri of E2 minus ds3 Ri of E3. Okay, so, that is the total surface force. Okay. Of course, on this volume there is a surface force. In addition, that there are volumetric forces as well. Okay. If you look back at the conservation equation that we had, these two are volumetric forces. Okay. This the rate of change of momentum is extensive, it depends upon the total volume. Okay. Similarly, this body force is extensive, it depends upon the total volume, whereas this depends only upon the surface area. Okay. So, my momentum conservation equation in general contains these three terms, two of which depend upon volume and the third depends upon the surface area. Okay. Now, if you take the limit, okay, as these all go to 0, okay, so this is delta x2, this is delta x1, this is delta x3. Okay. If you take the limit as these all go to 0, you can see that the volumetric terms, the rate of change of momentum as well as the body force, they will decrease as the cube of the length, because the volume is proportional to delta x1 times delta x2 into delta x3. Okay. So, the limit as these three go to 0, the volumetric terms will vary as the cube of the length, they will go to 0 as delta x cubed. Okay. Surface terms, on the other hand, will go to 0 as delta x square. Okay. As delta x goes to 0, delta x cubed goes to 0 much faster than delta x square, okay, because the ratio of the surface to volume goes to infinity as delta x goes to 0. Okay. So, as this volume goes to 0, delta x cubed goes to 0 much faster than delta x square, which means that I can the momentum conservation equation with these volumetric and the surface terms will continue to be valid in the limit as delta x goes to 0 only if all three terms go to 0. Okay. Obviously, the volumetric terms are going to 0 as delta x cubed, surface terms are going to 0 as delta x square. So, the only way that you will be able to retain a balance is if this thing goes to 0 as delta x goes to 0. In other words, I should be able to reduce this surface force into a volumetric form. Okay. That is the only way that I can ensure that, because the surface terms go to 0 as delta x square and the volumetric terms go to 0 as delta x cubed, the ratio goes to infinity unless for each and every differential volume element this thing goes to 0 in the limit as delta s goes to 0. Then the terms proportional to surface area will go to 0 and you will still be left with volumetric terms. Okay. Now, so if this has to go to 0, if this has to go to 0, then what is the condition? Okay. So, let us ask the condition, if this is equal to 0. Okay. Now, you know that this unit normal n1 and this unit normal n to the surface has three components, n1 E1 plus n2 E2 plus n3 E3. Okay. N1 is the angle made by the unit normal with the x1 x1 direction. Okay. N1 is the angle made by the unit normal with the x1 direction. Now, this angled surface area perpendicular to N1, the surface on the x2 x3 plane, that is this surface with unit normal in the E1 direction ds1, it is perpendicular to the E1 plane. Okay. So, therefore, since the angle between n vector and E1 is the same as the angle between ds and ds1, okay, I can write ds1 is equal to n1 ds, okay, because the angle between ds1 and ds1 is in the x2 x3 plane, ds is the actual slanted surface. Okay. The angle between those two is the same as the angle between the unit normals to those two, n and E1. Okay. Angle between them, the cos theta of the angle between n and E1 is just n1, that also has to be equal to ds1 by ds. Okay. Similarly, ds2 is equal to n2 ds and ds3 is equal to n3 ds. Okay. the angle between the surface S and the x2 x3 plane in the x1 x2 plane is the same as the angle between n and E3 and so on. Okay. So, I can use this, okay, to simplify, okay, and I will write this entire expression as total surface force is equal to ds into Ri of n minus n1 Ri of E1 minus n2 Ri of E2 minus n3 Ri of E3 is equal to 0. Note that n1 Ri of E1 is the force acting at a surface perpendicular to the x1 direction, Ri is of E2 is the force acting at a surface perpendicular to the x2 direction, Ri of E3 is the force acting perpendicular to the x3 direction, okay. And these three have to be equal to 0. That means that Ri of n is equal to Ni n1 Ri of E1 plus n2 Ri of E2 plus n3 Ri of E3. Okay. Ri of E1, force in the I direction acting at a surface whose unit normal is in the E1 direction. Okay. This I can write it as Ti1, where Ti1 is the force in the I direction acting at a surface whose unit normal is in the 1 direction. Okay. Ti1 times n1 plus Ti2 times n2 plus Ti3 n3. This in initial notation is just this second order tensor dotted with the unit normal. Okay. So, as I said, one can always write the force acting at the surface in this form as a second order tensor dotted with the unit normal. Okay. Okay. Tij is the stress tensor. Okay. As I have defined it over here, Tij is the stress tensor. Tij is equal to force per area in I direction. After all, I was the direction of the force there. Okay. Force per area in the I direction acting at a surface with outward. Note that we have defined the forces with respect to outward unit normal in this. Okay. In the j direction. Okay. So, that is the stress tensor. Okay. Surface force can always be written as Tij times Nj. Okay. So, when I write the surface force as Tij times Nj, then the integral of the surface ds of Ri is equal to integral ds of Tij Nj. This can now be reduced to a volume integral using the divergence theorem, ds partial by partial xj of Tij. Okay. I am sorry, this is the volume. And if I can reduce it to volume integral, all the other terms in the conservation equation also decrease proportional to the volume, and therefore, the balance, the dimensionality of the entire equation is maintained. Okay. Okay. So, this gives me an expression for the surface force. Okay. Back to my momentum conservation equation, integral v of t integral dv of rho ui is equal to integral dv of rho ai plus integral ds of Ri surface. Expand this out using the Leibniz rule on the left hand side, integral dv of partial by partial t of rho ui plus integral of the surface ds of nj rho ui uj is equal to integral dv of rho ai plus integral ds. Now, we write this in terms of the stress tensor dotted with the unit normal Tij and j. Okay. I have two surface integrals here of the unit normal dotted with something integrated over the surface, convert them both into volume integrals. Okay. Convert them both into volume integrals. Everything now is a volume integral, and this has to be true for any volume. It has to be true in the limit as the volume goes to 0, and what that implies is that the momentum conservation equation is partial by partial T of rho ui plus partial by partial xj of rho ui uj So, that is the momentum conservation equation. If I write it back in vector notation, it will be partial by partial T of rho u vector plus divergence of rho u u is equal to rho a vector plus divergence of the second order tensor. I prefer not to write it in this form because this, for example, is confusing. Does not tell you whether the divergence is to be taken with respect to the first index or the second index, okay. Whereas written in this form, it is very clear, okay, that the divergence is to be taken with the second index. Okay. I can expand this out. Okay. So, the first two terms I can expand it out as ui into partial rho by partial t plus partial by partial xj of rho uj plus rho okay. Just using the product rule for differentiating these equations. Okay. So, this is equal to rho ai plus partial by partial xj of Tij. Okay. And of course, partial rho by partial t plus partial by partial xj of rho uj, partial rho by partial t plus divergence of rho u is just equal to 0 from the mass conservation equation. Okay. So, this is equal to 0 from the mass conservation equation. Okay. Therefore, this momentum equation can also be written as rho into partial ui by partial t plus is equal to where Tij is the stress tensor. Okay, Tij is the stress tensor. So, that is the mass conservation equation. I am sorry, that is the momentum conservation equation in the x direction. Okay. Now, from the momentum conservation equation, it does not tell us exactly what form of the stress tensor is. For that, we have to write down a constitutive relation. However, we can get some information about the properties of the stress tensor by looking at the equation for the conservation of angular momentum. Okay. Angular momentum r cross f, I am sorry, r cross the linear momentum. Okay. So, I can write angular momentum as okay, if I have some coordinate system, the angular momentum of this entire volume about some fixed reference frame around some fixed coordinate has to be conserved. Okay. Without loss of generality, I can take this coordinate as the origin of my coordinate system. Okay. And then I would define angular momentum as the distance from the origin, the vector displacement from the origin crossed with rho u. Okay. It's equal to x cross rho u, okay, where x is the displacement vector from the origin. Okay. In indicial notation, I can write this as epsilon I j k x j rho u k. Okay. And the angular momentum conservation states that the rate of change of angular momentum is equal to sum of applied torques. The rate of change of angular momentum is equal to sum of applied torques. Okay. So, rate of change of angular momentum, okay, d by dt, integral of the volume, which is a function of time, dv of epsilon I j k x j rho u k, okay, is equal to integral over the volume of epsilon I j k x j times rho a k, that is the torque due to the body force, okay, the torque due to the body force, plus the torque due to the surface force, ds of x j times the surface force r k. Okay. Okay. Note that when I take the cross product, I have taken epsilon I j k times x j, x with u. So, the second index j is on x, third index k is on u. Similarly, on the right hand side, second index j is on x, third index is on the acceleration or the force in the final expression. Okay. And from my expression for the surface force in terms of the stress, I know that this has to be of the form epsilon I j k x j t k l n l. It has to be of the form t dot n, and I have to choose indices which are new for each dot product, because if I use the same index j or k for this last dot product, that index would appear more than 2 times and it result in an incorrect equation. Okay. So, simplify the left hand side first. Okay. So, I know how to simplify this quite easily, okay, using the Leibniz rule, dv partial by partial t of epsilon I j k x j rho u k plus integral over the surface of u dot n times this whole thing. Okay. U dot n times this whole thing, I have to use a new index here for u. So, this becomes u l and l times epsilon I j k x j rho u k, okay, is equal to integral of the volume dv of epsilon I j k x j rho e k plus integral ds epsilon I j k x j t k l n l. Okay. Convert the surface integrals into volume integrals using the divergence theorem. Okay. And also use the fact that epsilon is independent of time, x is also independent of time, because position and time are independent coordinates. Okay. So, then I will get integral of the volume of epsilon I j k x j partial by partial t of rho u k plus integral of the volume of partial by partial x l of epsilon I j k x j rho u k u l. Okay. Is equal to integral dv of epsilon I j k x j rho u k plus integral dv of partial by partial x l of epsilon I j k x j t k l n l. Okay. Okay. in this equation I use chain rule for differentiation. Okay, I use chain rule for differentiation, and I'll get integral over the volume of epsilon I j k x j partial by partial t of rho u k plus integral dv epsilon I j k. Okay. Now, in this term here I have one derivative with respect to this and the other derivative of what is remaining, okay, rho u k u l. So, I can separate out those two. Okay. So, I will write this as epsilon I j k times x j partial by partial x l of rho u k u l, okay, plus rho u k u l partial by partial x l of x j. Okay. And on the right hand side I have integral dv epsilon I j k x j rho u k plus integral dv. Once again I use the chain rule for differentiation, epsilon I j k into x j partial by partial x l of t k l plus t k l partial x j by partial x l. Okay. So, now in this partial by x j by partial x l, partial x, if j is 1 and l is 1, it is 1, if j is 1 and l is 2, it is 0. If j and l are the same, it is 1, if j and l are different, it is equal to 0. Okay. So, this I can write it simply as partial x j by partial x l is just equal to delta j l. Okay. Similarly, on the left hand side I have partial x j by partial x l, which is also equal to delta j l. Okay. So, both of these are equal to delta j l. Okay. Plus integral dv delta j l times u k u l gives me rho u k u j. Okay. Okay, gives me rho u k u j, delta j l times rho u k u l. Okay. Is equal to the left hand side is equal to integral dv epsilon I j k x j rho u k plus integral dv of epsilon I j k x j partial by partial x l t k l plus epsilon I j k t k l times delta l j l is just t k j. Okay. It's been a complicated derivation so far, but I have gone through this to make a point, an important point at that. Okay. I won't be able to complete it this lecture, but I will continue it in the next lecture. I will go through the same derivation, okay, to give you what the final point is regarding the stress tensor, as we will see that this angular momentum conservation equation shows that the stress tensor is symmetric. Once we have that, then we can proceed to find out constitutive relations for the stress tensor. So, kindly go through this derivation once again, and we will continue it in the next lecture. We will see you then.